Welcome to Chapter 2 of the Chiral Phonons series. In this chapter, we'll explore chiral phonons in real materials, starting with two-dimensional transition metal dichalcogenides and extending to three-dimensional chiral crystals. We'll examine how material symmetry enables phonon chirality and discuss the fascinating valley-phonon coupling mechanisms. By the end of this chapter, you'll understand TMD monolayer structure and symmetry, valley-phonon coupling mechanisms, optical selection rules for chiral phonon excitation, properties of 3D chiral crystals like alpha quartz and tellurium, chirality-induced phonon band splitting, and temperature effects on chiral phonon populations. Let's start with transition metal dichalcogenide monolayers, which have the chemical formula MX2. The structure consists of an XMX sandwich, where a metal atom M is sandwiched between two chalcogen atoms X in trigonal prismatic coordination. The metal can be molybdenum or tungsten, and the chalcogen can be sulfur, selenium, or tellurium. The point group symmetry is D3H. The D3H point group contains several important symmetry elements. From the trigonal prismatic structure, we get a threefold rotation axis C3, three vertical mirror planes, and a horizontal mirror plane. Crucially, inversion symmetry is broken in these monolayers, which is the key requirement for non-zero phonon angular momentum. Here are the key TMD materials and their properties. Tungsten diselenide WSE has a lattice constant of 3.32 angstroms and a bandgap of 1.65 electron volts. Molybdenum disulfide MoS2 has a lattice constant of 3.19 angstroms and a bandgap of 1.88 eV. Molybdenum diselenide and tungsten disulfide complete the family. All of these materials exhibit E' and E" chiral phonon modes at the gamma point. At the gamma point, the doubly degenerate E' and E" modes can be decomposed into chiral eigenstates. E+ equals the linear combination of EX plus I times EY divided by root 2, carrying angular momentum plus H bar. E- is the opposite combination with minus H bar. These represent atoms executing circular motion in opposite directions. The E' mode in WSE has a frequency around 250 to 260 wavenumbers. This is an in-plane optical mode, where the metal and chalcogen atoms vibrate in opposite directions within the plane. When decomposed into the chiral basis, atoms execute circular motion with well-defined angular momentum Lz equals plus or minus H bar. A unique feature of TMD monolayers is the valley degree of freedom. The hexagonal Brillouin zone has two inequivalent high symmetry points, K at plus K and K' at minus K. These are time-reversed partners with opposite Berry curvature. The valley index acts as a pseudospin that can be selectively addressed with circularly polarized light. Valley-phonon coupling creates a remarkable connection between valley index and phonon chirality. At the K-valley, sigma plus circularly polarized light couples to transitions involving E+ phonons with right-handed circular motion. At K', sigma minus light couples to E- phonons with left-handed motion. This is the origin of valley-locked chirality. The selection rules can be summarized in a table. Sigma plus light at the K-valley excites electrons with angular momentum plus H bar, which couples to E+ chiral phonons. Sigma minus at K' gives minus H bar coupling to E- phonons. These rules arise from angular momentum conservation in the photon-electron-phonon interaction. The physics underlying valley chirality locking comes from three mechanisms. First, angular momentum conservation requires the sum of photon, electron, and phonon angular momenta to be conserved. Second, D3H symmetry constraints dictate allowed transitions. Third, the valley-dependent deformation potential couples specific phonon modes to each valley. These selection rules lead to observable experimental signatures. In circularly polarized Raman spectroscopy, we see intensity asymmetry between sigma plus and sigma minus excitation at a given valley. Valley photoluminescence shows polarized emission locked to excitation helicity. Intervalley scattering between K and K' is mediated by specific chiral phonon modes. Intervalley scattering provides a key mechanism for chiral phonon involvement in transport. A carrier at valley K with N phonons can absorb an E- phonon to scatter to K' with N-1 phonons. The reverse process is also possible. These scattering events conserve angular momentum and require large momentum transfer, making them temperature-dependent. Now let's move beyond 2D materials to explore chiral phonons in 3D bulk crystals. We'll examine alpha quartz, tellurium, selenium, and chiral organic crystals. In these systems, structural chirality arises from the crystal lattice itself, not just broken inversion symmetry. The first observation of chiral phonons in a 3D crystal was reported by Zhu and colleagues in Science in 2018, studying alpha quartz. Alpha quartz crystallizes in chiral space groups P3121 for right-handed crystals or P3221 for left-handed. These space groups contain screw axes that give rise to structural chirality. Natural quartz exists as both enantiomorphs. Screw axis symmetry combines rotation with translation. An n-fold screw axis involves rotation by 360 over n degrees, followed by translation of m over n times the unit cell parameter c. The 3-1 axis in right-handed quartz involves 120-degree rotation plus 1/3 c translation, forming a right-handed helix. The 3-2 axis forms the opposite-handedness. Experimental evidence for chiral phonons in alpha quartz comes from circularly polarized Raman spectroscopy. Researchers observed non-zero Raman circular intensity difference, IR-IL, for specific phonon modes. This chirality persists up to 573 degrees Celsius, where alpha quartz transforms to beta quartz. Above the transition, the chiral signal disappears because beta quartz has a Chiral symmetry. Tellurium and selenium are elemental semiconductors with intrinsic structural chirality. Both crystallize in space groups P3121 or P3221, consisting of helical atomic chains. Tellurium has strong spin-orbit coupling, leading to interesting spintronic properties. Both materials exhibit chiral phonon modes of A1, A2, and E symmetry. The structural chirality of tellurium and selenium leads to unique physical phenomena. The circular photogalvanic effect generates photocurrents that depend on light helicity. A phonon Hall effect can arise from chiral phonon transport. Some researchers have described valley-like behavior in these 3D systems, analogous to 2D TMDs, but with fully three-dimensional character. Chiral organic crystals offer another platform for studying phonon chirality. Examples include crystals of L and D amino acids, helicines with inherent molecular chirality, DNA crystals, and chiral metal-organic frameworks. These materials combine molecular chirality with lattice chirality, often have low-frequency phonon modes accessible by THC spectroscopy, and offer chemical tunability. Now let's examine how chirality affects phonon band structure. We'll discuss chirality-induced band splitting, the phonon dispersion of WSE2, and the distinction between acoustic and optical chiral phonons. In chiral materials, phonon bands can split based on chirality. The frequency of left circularly polarized phonons omega plus differs from right circularly polarized omega minus at generic wavevectors. This is analogous to Rashba spin splitting in electronic systems. The splitting provides a signature of chirality throughout the Brillouin zone. In WSE2, the phonon dispersion shows distinct regimes. At the gamma point, left and right chiral modes are degenerate. At K and K', valley-dependent effects emerge due to the circular polarization of the phonon eigenvectors. The magnitude of any splitting is material-dependent and should be verified against first principles calculations or experimental data. At generic wave vector q away from high symmetry points, the polarization character varies with wave vector. Chiral phonons span different frequency ranges. Acoustic modes near the zone center have frequencies approaching 0. Optical modes at 200 to 400 wave numbers include the E' and E" modes we've discussed, which are the primary carriers of phonon angular momentum in TMD monolayers. High-frequency modes above 1,000 wave numbers involve molecular scale vibrations in organic systems. The assignment of chirality to specific modes requires careful analysis of the phonon eigenvectors. Temperature plays a crucial role in chiral phonon physics. We'll examine thermal population statistics, effects on valley dynamics, anharmonic phenomena, and phase transitions that can destroy chirality. Chiral phonons obey Bose-Einstein statistics. The thermal population n equals 1 over the exponential of h bar omega over kT minus 1. At low temperature, phonon population is exponentially suppressed. At high temperature, the classical limit gives n approximately kT over h bar omega. For the E' mode in WSE at room temperature, the population is partially excited. Temperature strongly affects valley dynamics through phonon-mediated scattering. The intervalley scattering rate gamma is proportional to the phonon occupation number n of omega E valley coherence lifetime tau v is inversely proportional to this rate. At 300 Kelvin, E' modes with equivalent temperature around 360 Kelvin are partially populated, enabling significant intervalley scattering. Anharmonic effects become important at elevated temperatures. Frequency softening causes omega of t to decrease from omega 0 by an amount delta omega. Line width broadening increases gamma of t, reducing phonon lifetime. 3-phonon mixing processes can degrade phonon chirality by coupling left and right modes. These effects generally reduce chiral signatures at high temperature. Structural phase transitions can destroy phonon chirality entirely. Alpha quartz transforms to beta quartz at 573 degrees Celsius. The alpha phase has space group P3121, while beta quartz has space group P6422. At the transition, the phonon spectrum reorganizes and chiral phonon signatures change abruptly. This is accompanied by soft mode behavior as the transition is approached. Let's now discuss computational approaches to studying chiral phonons. We'll look at Python implementations for modeling TMD materials, including parameter classes, Bose-Einstein functions, and the valley phonon coupled Hamiltonian. These tools allow quantitative predictions of experimental observables. The valley phonon coupled Hamiltonian can be represented as a 4x4 matrix in the basis of K-valley spin-up, K-valley spin-down, K'-valley spin-up, and K'-valley spin-down. The matrix elements include valley splitting, phonon coupling, and spin-orbit terms. For WSE2, we can use experimentally measured parameters to construct this Hamiltonian. Simulation results for WSE2 show the valley phonon dispersion from gamma to K at room temperature. We find approximately 0.4 phonons thermally excited per mode. The temperature-dependent scattering rate shows an exponential increase with temperature, consistent with Bose-Einstein statistics governing the phonon population. Comparing materials, we can plot phonon frequency versus material type. 2D materials like WSE2 and MO-S2 show chiral modes in the 200 to 400 wave number range. 3D materials like alpha quartz have modes across a wider frequency range. Tellurium has particularly low-frequency chiral modes due to its heavy atoms and weak interchain bonding. Let's summarize Chapter 2. In 2D TMDs, D3H symmetry and broken inversion enable valley-locked chiral phonons. Valley selection rules couple sigma plus and sigma minus light to opposite valleys and phonon chiralities. 3D chiral crystals with screw axis symmetry support chiral phonons throughout the bulk. Phonon dispersion shows chirality-induced band splitting. Temperature effects include thermal population and anharmonic degradation of chirality. In Chapter 3, we'll explore experimental detection of chiral phonons. Topics include circularly polarized Raman spectroscopy, circular dichroism measurements, ultra-fast spectroscopy techniques, and optical selection rules. We'll see how these methods have been used to verify the theoretical predictions discussed in Chapters 1 and 2. See you in the next chapter.